In this section, we're looking at freely falling bodies, which is basically like an acceleration in the vertical direction. So things that are falling or being thrown upward. So first of all, this is going to revolve around gravity. So anytime that we're looking at the acceleration in these problems, it's always going to be gravity of whatever planet we're on. So for the most part, we'll be dealing with Earth. So gravity, not just a good idea, but it's the law. So this has been proven over and over again. So it is a scientific law. So in free fall, this means that an object is only being pulled by gravity, and we are going to not count air resistance. In most problems in real life, you would have to account for air resistance, but we are not going to do that in our problems because that's just too much math for us right now. So for gravity on Earth, we're going to use G instead of A. We'll often use G, or we could just use A. Either one is fine. 9.8 meters per second squared. So if something is falling towards Earth, that's going to be a positive number. If the object is being thrown upward away from Earth, the object would be slowing down as it rises higher, so that would be negative 9.8. If we put that in terms of feet per second squared, it's going to be 32.2 feet per second squared. So if we look at this, if that 9.8 was rounded to 10, basically that means for every second that an object falls, it's going to speed up 10 meters per second. So after 1 second, the object would be going 10 meters per second. After 2 seconds, the object would be at 20 meters per second, and so on. So at 3:30. And again, this is if we're rounding that 9.8 to 10. In our problems, we will use 9.8, so it'll be more exact. So if you're familiar with the Roadrunner and Wile E. Coyote, often when he is getting ready to fall, they're neglecting gravity. So he runs off the cliff, and then he kind of hangs there for a while. So in real life, you would immediately start to fall. So he's kind of breaking the laws of gravity there in his cartoon. We're also going to look at what are called projectiles, which basically are objects flying through the air. So we'll look at objects that we are dropping straight down, objects that are thrown straight up, and then objects that are thrown kind of across. So if we look at this though, all of the intervals as the objects move down increase the same amount because they have the same pull of gravity. So even from here to here, here to here, and then here to here is the same distance. And then each interval down is more and more based on the fact that it's speeding up more as gravity pulls it down. So when you're thinking about objects being thrown up into the air, you have to remember what goes up stops at the top. So its velocity at the top is 0, then it comes back down. So if we're throwing something, whatever its initial velocity is at the bottom, once it gets to the top, the final velocity is 0. When it's coming down, that initial velocity is 0, and then its final velocity at the bottom is going to be whatever it was when you initially threw it up. So let's say it's 20 meters per second, 0 at the top, 0 at the top, and then 20 meters per second down at that same level. All right, so as we look at this problem, it says a stone is dropped from rest from the top of a tall building. So we can go ahead and write drop from rest. So our VI, we know is 0. After 3 seconds of free fall, so our time is 3 seconds. What is the displacement of the stone? So we're looking for displacement. So in this, it looks like we only have 3 variables, but remember when we're using these equations, we need 4. But it does say that it's dropped and it's in free fall, so that tells us that our acceleration is 9.8. So a lot of times in these problems, you'll have to remember that because it's not going to come out and straightforward tell you the acceleration. So we'll go back to our equations here. We have VI, T, D, and A. We do not have VF. So for that, we'll have to use this the third equation, D equals VIT plus 1/2 AT squared. So we'll do D equals VI T plus 1/2 AT squared. So if I plug that in, D equals, if VI is 0, this whole part will cancel out. So I'm going to do 1/2, A is 9.8, and then T we said is 3. So if we solve that for D, we get 44.1 meters. Then the next part of the problem asks us its final velocity just before hitting the ground. So now we're looking for VF. We're going to use that same information, all of the info we had before. So we can really use any equation at this point. Probably the easiest one is going to be this top one, VF equals VI plus AT. So if we do VF equals VI plus AT, and again, VI is 0, so that's going to cancel out. So VF equals 9.8 times 3. So VF will just be 29.4 meters per second. On the next problem, it says a football coin toss. We've got a coin flipped, thrown in the air with an initial speed of 5 meters per second. So VI is 5 meters per second. In the absence of air resistance, how high does the coin go above the point of release? So if we look at this, in a coin toss, you're going to have that coin start in someone's hand. It's going to be flipped up into the air to some point, to whatever point that it's going to slow down till stop. So that velocity at the top will be 0, and then it's going to come back down. So it asks, how high does the coin go above its point of release? So that point of release, we're looking for the distance there. So if we know that the VI at the bottom is 5, the VF at the top, where it's slowed down to the point of stopping, is 0. So we can say VF is 0. We're looking for D. And the other variable that they don't tell us, but we know, acceleration, is 9.8. But also, it's slowing down, so it's going up in the air, so it's going to be a negative 9.8. So looking at our equations, we don't have T. So again, we're going to use that last one. So VF squared equals VI squared plus 2AD. VF this time is 0. And our VI is 5 plus 2. A is negative 9.8. And we're solving for D. So when we solve for D, we end up getting 1.28 meters. So the last part of this problem, it says, what is the total time the coin is in the air? So we just solved the distance for it going up, but it wants total time in the air, so that would be going up and then coming back down. So when we do this, we're going to do solve for the time and then double it. So using the information we have, we'll use the VF equals VI plus AT equation. And then once we get T, we'll double that. So VF we said is 0, VI 5 plus the negative 9.8 t, and that'll be the time to get to the top. So that turns out to be t equals 0.51 seconds. So we're going to double that. So the total time, I'm going to do t sub t for total time, would just be 1.02 seconds.